In this video, I'm going to show you how to use and enter scientific notation on a TI graphing calculator. I'm going to use a chemistry problem that's very often seen on AP exams as my method of showing it. You don't have to worry about the chemistry involved. Just make sure that you can do the same type of calculation on your TI. Let's start off with the problem. Here we've got yellow light with a wavelength of 565 nanometers. Light is composed of photons, and they have a specific wavelength. In this case, it's given in billionths of a meter. That makes the number easy to use, nanometers. That's pretty typical right now for measuring wavelengths of light. And the question is, what's the energy of a single photon of the yellow light? So we've got little bundles of energy that are defined by quantum, and those are called photons. So we're going to find their energy. Now on the AP exam, you're given a set of equations, and this is the set of equations that you'd use to solve this problem. It involves energy, in this case the energy of the photon, frequency, which is symbol nu, lambda, which is symbol wavelength of these photons. The frequency is how many of these photons go by in a second. You're given a couple of constants associated with this, Planck's constant, which is this h, and the speed of light, which is c. And here's our energy is equal to h times the lambda, which is the frequency. Now, if you remember, our question didn't give us the frequency of light, it gave us the wavelength of light. Well, the wavelength of light here is involved in this equation. So this is the first equation that we're going to use. Once we get our lambda, then the next step will be to determine the energy of that photon. So back to our problem. Here it is. We'll get our equation out. C is equal to our lambda times nu. We'll start off by changing that equation and manipulating it so that we can solve directly for nu, where we take our constant, one of the important constants, the speed of light, divided by, in this case, the wavelength, lambda 565 nanometers. We'll set that up. The speed of light is given on the equation sheet. They give it to 2.998. I typically use 3, but we'll use their 2.998 meters per second. We've got that superscript -1 divided by our lambda wavelength, which is here 565. And again, if I was answering an FRQ question, I'd show the setup that I have 2.998 speed of light times 10 to the 8th. That's quite a large number, meters per second. Now, there's a problem with this division because we have meters here and nanometers here. Now, n is a prefix, and it stands for a number, and it stands for 10 to the -9, which is where all this comes in for using our calculator. Here we've got our calculation that we need to put in. We've got our speed of light divided by the wavelength. They're both in meters, and our answer, because the meters cancel out, will be per second. And frequency is how many waves per second. So that's perfect. We've got our units correct, and we can get our frequency calculated correctly. A common error is to forget about this n. Don't. It's an important number. So time to pull the TI calculator out. And here it is. I've got it, and we'll put that calculation in. Again, I just use 3, but let's be very, very compulsive and make this 3.998. And this is where we have to put our times 10 to. And this is where a common error is made. A lot of people will see the times 10 to next to the logarithm button here. It's a 10 raised to the x. Don't use that. On any calculator, if they have a log and a 10 to the x, that's not what you're going to use. We'll just use this when we go to pHs and anti-logs. You don't want to use that. Instead, this is on TIs the key thing that stands for times 10 to. It's EE. Unfortunately, it's a second function button, but I wish they didn't have it that way. I would have preferred the EE rather than the comma, but hey, we can hit second function EE, and you'll see E, and that becomes part of the number. That stands for times 10 to, and now we've got our number here, which is 8. So good, we've got our 2.998 times 10 to the 8, and we're going to divide that by, okay, divided by, and then I've got my 565. And again, remember, you'll be doing this a lot on your calculator. Second function, EE, will become second nature to you, times 10 to. Another possible error is you can see this minus. This minus that is on the TI is really for subtraction. You don't use that. You'll get a error message. Instead, you're going to use the parentheses minus, which stands for the negative sign. And in this case, it's going to be -9. Now, the AP exam now allows you to use the calculator both on multiple choice and on the FRQs. And I mean, that's very nice. You can do calculations quickly, but don't do them quickly. Think about them. You put these numbers in. If you made one number wrong here, everything's going to be messed up. So check your numbers, okay? 2.998. I know that you're limited in time on the exam, but if you get wrong answers, you've wasted your time. And I've got the 565 times 10 to the -9. And think about it. Think about the answer. I've got this e to the 8, this large number, and we've got millions, divided by a very, very small number. I mean, when you write e to the 9, it's very easy to write that down, but this is a small number. I mean, this is a microscopic level. This is the size of a single wavelength of yellow light. And we're dividing a large number by a very, very small number. We should get a big answer. Let's enter and let's hope we get a big answer. Indeed, we do. Here it is, 5.30619469, impressive number, times 10 to, that's what this E stands for, to 14. And that makes sense. We've got these minuscule waves of yellow light, these little photons, going by us at the speed of light. So the number of them is going to be huge. These minus things going by speed of light, I mean, try and count that. And, well, it can be done. 5.3 times 10 to the 14 waves going by in a second. Now, this is our first part of an answer. Let me get back to the sheet. I'm not going to write it out. I'm just going to leave it here. If this was an FRQ, you have gotten this and shown this, you probably get a point for this type of problem. It would be the equivalent of 2 points for a problem like this. One is to find out the frequency, our nu, and the other is to get the energy. You would certainly have this shown on your FRQ. Now we're going to go to the second part, where we're going to find the energy itself. We're going to get this energy of one of these single photons. This is the smallest unit of energy, the quantized energy that you can get with yellow light. I mean, when you are trying to measure yellow light, this is the smallest part you can get. That's why it's called a quantum. Originally, Max Planck, who got the Nobel Prize for this, thought this number was going to be 0. In fact, this H sort of stands for a throwaway constant. But he found out that it was an actual value, that quantized energy. And we're going to take that H. Let's see, where is it here? There it is, 6.626. It's carried out a few more numbers, and it's a defined value. Now, in fact, it's even used a defined mass. It's a very important constant, 6.62 times 10 to the -34. And we're going to multiply that times our frequency. E of 6.62 times our answer that we have here. So I'm going to get my calculator, and I'm going to type in Planck's constant. 6.626. I'm double checking. It's easy to miss these numbers up. And again, times 10 to. Don't type in times 10 to. No, 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 no. Don't type times 10. Don't type this second function log. EE. And then negative value 34. I'm going to multiply that times my frequency. Don't type in this number. You have a chance of getting it wrong. You're going to be wasting time typing it in. You can just simply type second function answer. Multiply our Planck's constant times our answer. Now, again, we think. Here's a negative 10 to the -34. 10 to the 14. We're still going to get a small number. And you'd expect that. A single smallest energy possible of a yellow light is going to be a small amount of energy. A very small amount of energy. Here it is. 3.5158846 times 10 to the -19. And energy is measured in joules. And No, this I didn't bother to type in. That's sort of like, no, didn't even bother. So what is that energy? That energy, please do me a favor and yourself a favor and don't type in this huge long number. That's ludicrous. We only knew the wavelength as 3 significant digits, 3 values. This wasn't 5.65000. We knew it to a limited amount of accuracy, and therefore this has a limited amount of accuracy. Typing this entire number in will make a AP reader say, what's wrong with this person? Who do they have for a chemistry teacher? No. All you need is 3 significant digits here. All you got to type in is 3.52 times 10 to the negative 19. I'll pull my calculator out to make sure I didn't make a mistake. 3.52. And my unit is joules. For energy, it's important because a lot of energy values are in kilojoules. We took this second and multiplied by per second, and we've got joules left behind. Our answer makes sense. A small amount of energy for this single photon. And again, please don't write out the entire number. Save your graphite. You don't have to write that whole thing out. Save some time. Show that you know a little bit about what numbers mean. In this case, this is the accuracy that we know for a single photon. So again, reviewing on your TIs. Use second function EE for times 10 to. Use the negative sign in case it's a small value. We now know how to use our TI graphing calculator. Remember how to enter scientific notation, and please be careful with significant figures and think when you do your calculations. Make sure your answers make sense. Okay, goodbye.